Initial value problems, elementary differential equations. In some applications, the constant of integration is of interest. In such cases, we can solve for the c if we are given a point that is a solution of the antiderivative. This point is called an initial condition or initial value. Example, suppose f prime of x equals 3x squared minus 6x and f of 2 equals 4. Find f of x. We find the indefinite integral f of x first. To do so, we apply that power rule. You'll get f of x is equal to the constant 3 times the antiderivative of x squared is 1 over the power of 2 plus 1, which is 3, times x to the power of 2 plus 1, which is also 3, minus for the second term 6 times, and then the antiderivative of x is 1 over 2, which is 1 more than the existing power, and x to the power of 2 plus c. Let's simplify that, and you'll get f of x equals 3 times 1/3, that's a coefficient of 1. So you got x cubed minus 6 times 1/2 is 3. So 3x squared plus c. We'll use the given initial value of f of 2 equals 4 in the indefinite integral we just obtained to get the value for c. We'll put in 4 for f of x, and to every place there's an x. So 2 cubed minus 3 times 2 squared plus c. We're going to solve for the c. Get 4 equals 2 cubed is 8, minus 3 times 2 squared is 12 plus c. And when you solve it, you'll get that c and 8 are the same. We will now replace the constant c with the value we just solved for. So you had f of x equals x cubed minus 3x squared plus c. We replace that c with the 8. Example, solve d squared y dx squared equals 1 over x cubed, given y prime of 1 equals 1/2 and y of 1 equals 1. The wording solve the d squared y dx squared means find the y, get to the y function. To begin, let's rewrite the d squared y dx squared as x to the power of -3. We'll solve for dy dx by computing the antiderivative of d squared y dx squared. Then you get dy dx is equal to, take the antiderivative of x to the -3, that'll be 1 over -3 plus 1, which is -2, times x to the power of -3 plus 1, which is -2, plus some constant. I'm going to call it c sub 1. We can simplify it and say dy dx is equal to the negative of 1 divided by 2x squared in the denominator plus c1. We'll use the initial condition y prime of 1 equals 1/2. That's for the first derivative to solve for c sub 1. So where dy dx was, that's y prime, we'll put in 1/2. And then every place there's an x in the derivative, we'll replace it with 1. So you've got -1 divided by 2 times where the x was, put in 1. 1 squared plus c sub 1. And arithmetically solve for c sub 1, which will give you 1. Now replace the constant c sub 1 with the value we just solved for, which we got 1. The derivative dy dx is equal to -1 divided by the quantity 2x squared plus 1. We'll start with that to solve for y. Let's rewrite the dy dx as -1/2, and we'll write it as x to the -2, because we can use the power rule for antidifferentiation there, plus 1. We'll solve for y by computing the antiderivative of dy dx. So y would be equal to the negative 1/2, the constant stays put. Then you've got 1 over the power plus 1. Negative 2 plus 1 is negative 1. X to the existing power plus 1. Negative 2 plus 1 is negative 1. Plus the antiderivative of 1 is x. Plus, don't forget, the constant. We'll call this one c sub 2. We'll clean it up a little bit. We've got negative 1/2 times negative 1. So we can have y equals 1 in the numerator divided by the quantity 2x. Since we had x to the minus 1, we'll just rewrite it as a positive x in the denominator, plus x plus c sub 2. Now, we'll use the initial condition y sub 1 equals 1 to solve for the constant c sub 2. Where y was, we replace it with 1, and every place there's an x, we replace that with 1 as well. So you get 1 equals 1 divided by 2 times 1 plus 1 plus c sub 2, and solve for c sub 2, which will give you negative 1/2. Now replace the constant c sub 2 with the value we just solved for. Then our solution is the function y equals 1 divided by 2x plus x minus 1/2.